This video is prepared by Aavya classes. Please subscribe the channel, raise your doubt and watch the video for sure success in JEE, AIMS and NEET. The problem based on the concept, and first problem is what is the maximum value of force F such that block shown in the arrangement does not move. Mu is equal to 1 by 2 square root 3. So for this we just first draw the free body diagram of system, and it's very easy that you just draw the free body diagram. In the downward direction we have force equal to n mg, in the upward direction we have force normal force, and this force external applied force which is making angle 60 degree with the horizontal direction will resolve into component. First is f cos theta in the horizontal direction, so f cos 60 degree, and f sin theta in the vertical direction. Now you just make a equilibrium. So for vertical equilibrium it's n is equal to, or in fact n minus mg minus f sin 60 degree is equal to 0. From there we get n is equal to mg plus f sin 60 degree. Just put the value of m is equal to square root 3 g, and f is equal to, you have to calculate f. So this is our equation 1. Now for horizontal equilibrium, if you see that when this object moves, then a frictional force will be developed, and the value of this frictional force is equal to mu into n. So for horizontal equilibrium, f cos 60 degree is equal to mu n is equal to mu into square root 3g plus f into square root 3 by 2. Here mu is given as 1 by 2 square root 3. So f into 1 by 2 is equal to g by 2 plus f into 1 by 4. From there we get f into 1 by 4 is equal to g by 2, and f is equal to 5 divided by 1 by 4, that is equal to 20 Newton. So answer A equal to 20 Newton is correct. Now we will see the problem 2. A block of mass m rests on a rough horizontal surface as shown in figure. Coefficient of friction between block and the surface is mu. A force F is equal to mg acting an angle theta with the vertical side of the block pulls it. In which of the following cases the block can be pulled along the surface? So as usual, first we draw the free body diagram of system. This m mass is pulled with force equal to mg, making an angle theta with the vertical. So if I resolve this force into component, then f cos theta will act in upward direction, that is equal to mg cos theta, as f is equal to mg, and mg sin theta will act in horizontal direction. Now the force due to gravity is mg in downward direction, and the normal force is n in upward direction. The frictional force F is equal to mu n acting in along the surface in backward direction. Now we will make the condition of equilibrium. So for vertical equilibrium we have n plus f cos theta is equal to mg, that is n plus mg cos theta is equal to mg. From there we get n is equal to mg 1 minus cos theta. Now for pulling, the problem asks that block can be pulled along the surface. So for pulling, P must be greater than equal to, or we just write that for pulling mg sin theta must be greater than and equal to mu into n, mu into n is our limiting friction, the maximum value of a static friction, that is which is equal to mu into mg1 minus cos theta. So mg sin theta must be greater than and equal to mu mg1 minus cos theta. From there we get sin theta must be greater than and equal to mu 1 minus cos theta. The value of sin theta is equal to, as we know, a formula. Here the options are in terms of theta by 2 also. So what we will do, we just divide, we just write sin theta into component in this form. Sin theta is equal to 2 sin theta by 2 into cos theta by 2, and 1 minus cos theta is equal to 2 sin square theta by 2. So by using these formulas we get 2 sin theta by 2 into cos theta by 2 must be greater than equal to mu into 2 sin square theta by 2. So from there we get cot theta by 2 must be greater than equal to mu. So if you see the option, then option D is correct. Cot theta by 2 must be greater than equal to mu. So in this way we can solve this problem. Our approach is very simple. Just draw the free body diagram, calculate the value of n, that is normal force, and then apply the case for movement of block in the horizontal direction or the condition of horizontal equilibrium. Now we will see problem number 3. Now we will see problem number 3. A car is going at a speed of 6 meter per second square when it encounters a 15 meter slope of angle 30 degree. The friction coefficient between the road and tire is 0.5. The driver applies the brake. The minimum speed of car with which it can be reached at the bottom, and you have given 4 options, you have to calculate it. So first we will see that what will be the free body diagram of this system. So for convenient I am just drawing this diagram in this way. Suppose this is our 30 degree and this car is moving in this way. So here if I draw the free body diagram of system, then in the horizontal or along the plane in downward direction we have force equal to mg sin theta, and in the along the plane in the upward direction we have a frictional force, that is mu mg cos theta. So the acceleration along the plane is equal to mg sin theta minus mu mg cos theta. Now if we put it's a force along the plane. So if we have to calculate the acceleration along the plane, we will divide it by mass. So acceleration along plane is equal to g sin theta minus mu g cos theta. Solve it. Then A is equal to g sin 30 degree. G sin 30 degree minus mu g cos 30 degree, that is equal to 5 minus 10 into 1.73 divided by 4, 5 minus 17.3 divided by 4, 5 minus 4.33, and it comes equal to 0.67 meter per second square. So acceleration along the plane in downward direction is equal to 0.67 meter per second square. If this car moves for a distance equal to 15 meter with an initial speed of 6 meter per second, then we just apply this formula. V square is equal to u square plus 2as. V square is equal to u is given as 6, so 6 square plus 2 into a is 0.67, s is equal to 15 meter. From there we get 36 plus 30 into 0.67. That is 56.1. So v square is equal to 56 approximately, and v is equal to square root 56. So square root 56 is something around 7.5. Answer will be C, 7.49 meter per second. Now we'll move to next problem, and this is in fact very good. It's very conceptual problem. In case 1, the vase B is stationary and block A starts sliding when the angle of plane is greater than theta, while in case 2, vase B is moving upward with an acceleration a0 and block A starts sliding when the angle of plane is greater than alpha. Coefficient of friction between A and B in both cases are same. Then you have to calculate the relation between theta and alpha. So how we will solve this problem? See, in case 1, the object starts moving and this vase is stationary, so clearly theta is our angle of friction, and tan theta is equal to mu. Or in fact, if I draw the free body diagram, then mg sin theta will act in downward direction along the plane, and mu mg cos theta is the force along the plane in upward direction. So at the start of sliding, mg sin theta is equal to mu mg cos theta. So this is the point when this block actually starts sliding. So from there we get tan theta is equal to mu, which is our angle of friction. Now we see the second case. Here also in the downward direction, the force is equal to mg effective sin theta, and in the upward direction along the plane, the frictional force is equal to mu mg effective cos theta. So instead of g, here g is replaced by g effective, where in case of if the object is moving in upward, then g effective is equal to g plus a, and if the object is moving downward, then g effective is equal to g minus a. About it we have already learned in our previous classes. So if I make the condition for, or in case of limiting case, mg effective into sin theta is here, instead of theta it's our alpha, so just make sin alpha. So mg effective sin alpha is equal to mu mg effective into cos alpha. So on solving we get tan alpha is equal to mu. So clearly alpha is again tan inverse mu. So from equation 1 and equation 2 we may infer that theta is equal to alpha. Like if a object is placed in a lift moving upward or downward with some acceleration, no matters that wherever it goes, upward or downward, the coefficient of friction will remain same. This is the problem number 5. A block of mass m is equal to 2 kg is resting on a rough inclined plane of inclination 30 degree as shown in the figure. The coefficient of friction between the block and plane is mu is equal to 0.5. What minimum force F should be applied perpendicular to plane on the block so that block does not slip on the plane? G is equal to 10 meter per second square. So what you will do, you will again just draw the free body diagram of system, and from there you can solve it very easily. So all forces are shown here. In the downward direction along the plane we have mg sine theta. In the downward direction or in the upward direction along the plane we have a force mu into n, while the perpendicular to plane we have forces F and mg cos theta. Perpendicular to in downward direction and upward direction we have normal force. So equating the forces or equilibrium perpendicular to plane, n is equal to F plus mg cos theta, and from there we get n is equal to this is our equation 1. Now for equation 2 we just use the motion along the plane, that is along the plane, and for equilibrium mg sine theta is equal to mu into n, that is equal to mu into F plus mg cos theta. If we solve it we get F plus mg cos 30 degree is equal to mg sin 30 degree divided by mu. Value of m is equal to 2 and mu is equal to 0.5. So F plus 2 into 10 into square root 3 by 2 is equal to 2 into 10 into 1 by 2 divided mu is equal to 0.5. So we get F is equal to 20 minus 10 into square root 3, it is 20 minus 10 into 1, 732. So we get 2.68 Newton. So the minimum force will required in this case is equal to 2.68 Newton.